Dear students, in this video lecture, I am going to start with second unit. In second unit, you will be learning about single phase AC circuits and three phase AC circuits. First, we will take up single phase AC circuits. In single phase AC circuits, first we will have review of AC fundamentals, then analysis of AC circuits with the different loads such as RL, RLC connected in series and parallel. Then improvement of power factor using a capacitor in parallel with the given impedance. So we'll start with review of AC fundamentals. In the review of AC fundamentals, we will discuss about an expression for sinusoidally varying alternating voltage and current. Then RMS value, average value, form factor, phasor representation of RMS quantities, then phasor algebra, that is how to add two phasors or how to subtract one phasor from another phasor, and also how to multiply two phasors or how to divide a phasor by another phasor. So first we will start with review of AC fundamentals. We know expression for sinusoidally varying alternating voltage and current R V equal to Vm sin omega t plus or minus phi, and I is equal to Im sin of omega t plus or minus phi. Here V and I are instantaneous values of sinusoidally varying alternating voltage and current. Where V and I are instantaneous values of sinusoidally varying voltage and current respectively. Vm and Im are their maximum or peak values. Omega is angular velocity in radians per second. T is time in seconds. And phi is phase angle. For a sinusoidal voltage or current starting at 0 seconds, phi value will be equal to 0. That is, if I take voltage along y-axis and omega t along x-axis, then 0 time point will be here. For phi equal to 0, the voltage waveform will start at 0 time. This is for phi equal to 0. Maximum value of instantaneous voltage attained is what we call as Vm. If voltage waveform does not start at 0, then phi value will not be equal to 0. For omega t equal to non-zero value, the voltage waveform may start like this. In this case, the voltage waveform is not starting at 0, but it is starting after phase lapse of pi by 6 radian or 30 degree. So this gap here is nothing but phi on the omega t axis. If voltage waveform starts 5 radians late, voltage expression will become V equal to Vm sine of omega t minus phi. In this case, you can take phi as pi by 6 radians. Instead of starting late, the voltage waveform may start earlier also. That is, the voltage may start at this point on omega t axis. In this way. That means here the voltage has started 5 radians earlier, assuming Vm remains the same in all cases. Now we can write expression for this instantaneous voltage as V equal to Vm sine of omega t plus phi. Now can you say what will be the expression for instantaneous voltage that was shown starting at omega t equal to 0 in first figure? Here the expression for instantaneous voltage will be V equal to Vm sine of omega t only because phi is 0 here. Here also we will show maximum voltage as Vm. You have studied in your lower standards that after every pi radians, voltage or current waveform changes its direction. So we will write here pi, 2 pi, 3 pi and so on. But here it is phi, therefore here it will be now pi plus phi, and here it will be 2 pi plus phi, and here it will be pi minus phi, 2 minus phi, 3 pi minus phi. There exists relationship between angular velocity and frequency, that is, omega is equal to 2 into pi into f, where f is frequency in hertz, where f is frequency in hertz. You know that time required to complete one cycle by a alternating voltage or current waveform is called its time period. relationship between T and F. T is equal to 1 by F. T is measured in seconds. Next we will define what is average voltage and what is average current. Average value of an alternating voltage is defined as average of all its instantaneous values. For sinusoidally varying voltage, V average is equal to 0.636 times its peak value or maximum value Vm. Similarly, we can define average current IAV. Average value of an alternating current is defined as average of all its instantaneous values. For sinusoidally varying current, I average is equal to 0.636 times Im, where Im is peak or maximum current. Next we shall define RMS voltage and RMS current. RMS voltage is denoted by bold capital V, or you can make use of subscript RMS with this V. It is that steady voltage which produces same heating effect as produced by an alternating voltage when applied to the same circuit for same time duration. To understand let us consider the following circuit. In this circuit we are having now a resistor R which can be connected to sinusoidal voltage using switch S1 or DC voltage using switch S2. Now in this circuit, if I keep closed S1 say for t seconds of time, then alternating voltage will circulate alternating current I through the resistor R, and because of I square R losses, heat energy will be dissipated by this resistor R, and after t seconds of time I will open the switch S1 and I will close switch S2. Then DC source will circulate DC current I. If now switch S2 is kept closed for t seconds again and resistor R dissipates same amount of heat energy, then this DC voltage will become RMS value of this AC voltage supplied, because both of these are producing same heating effect in resistor R when supplied for same time t seconds. Note here, in the above circuit, when switch S1 is closed with S2 open, sinusoidal voltage will be applied to resistor R. Sinusoidal current I flowing through R will cause certain amount of loss of energy in the form of heat. Now, if S1 is opened and S2 is closed, DC voltage, nothing but steady voltage, will circulate I ampere of current through R and cause loss of energy in the form of heat. If loss of energy in both the cases is same, then DC voltage V is average value of sinusoidal voltage V. Remember that S1 and S2 should be closed for same time duration. That also we will make a note. S1 and S2 closure duration must be equal. This is very, very important. For sinusoidal voltage, V RMS is equal to peak voltage or maximum voltage divided by root 2, which is equal to 0.707 times maximum voltage. Now we will define what is RMS current. RMS current is denoted by bold letter I or letter I with RMS subscript. It is defined as that steady current which produces same heating effect in the same circuit in same time duration as that produced by alternating current. For sinusoidal current, I RMS is equal to peak current or maximum current divided by root 2, which is equal to 0.707 times peak current. Next we will define form factor. Form factor of alternating quantity is defined as ratio of V RMS to V average or I RMS to I average. For sinusoidal quantity, quantity means here voltage or current. Form factor is equal to V RMS by V average, that is equal to Vm by root 2 divided by 0.636 Vm that is equal to Im by root 2 divided by 0.636 Im. On simplification, form factor value becomes equal to 1.11. So for sinusoidal quantity, form factor is equal to 1.11. This form factor is important because we make use of this quantity in deriving the expression for voltage induced in transformer and alternator. Next we will define what is peak factor. Peak factor is defined as ratio of maximum value of alternating voltage to RMS value of alternating voltage or ratio of maximum current to RMS current. For sinusoidal quantity, peak factor is equal to Vm divided by V. V is Vm divided by root 2, that is equal to Im by root 2. On simplification, we get it as root 2. And we know that root 2 is equal to 1.414. So peak factor for sinusoidal quantity is 1.414. Dear students, I will stop the class here and continue in next class. Thank you.